In this video we're going to look at conjugate points on an ellipse which has been generated by an attractive force given by MUR. Now the equation we see here up at the top, we've derived that in a previous video, so if you're unsure where that comes from you can click on this video here and it goes through that derivation. But what we do is we rewrite this equation in this form here. Now there's a derivation of this equation as well at the end of this video, so if you hang on you'll be able to see exactly where that comes from. So that's the equation there of the ellipse. So if we were to take that off, you can see that's the ellipse there. Now what we have here is that ellipse, and we also have a conjugate point. Now the conjugate point will follow that ellipse round as we move it, and there's a line here, the blue line there, which is a tangent to that conjugate point. Now we've also got another line here which is tangent to this point here, which is in blue. Now you'll note that both of these lines, they meet at a right angle, okay, and at that point where they meet at the right angle and the crossover, that will be a point on a circle, and that's called the director circle. So let's shift this along to a different point. Okay, so if we shift we shift it up round there, so the ellipse move to that point there. Now what we can do is we can find this other point in the director circle by moving that little blue point, so the green line moves. Okay, so if I just shift this round to here, now it's a bit kind of minus 2.2, so it's minus 2.19, say it's roughly there, 2.18. So you can see that now we've moved this point round again, and we can note that at right angles there, both of these points meet. So when they cross there, both of the points meet again on this director circle. We could keep doing that. We can keep moving this ellipse round, and then we can keep positioning this other blue point, purple point, and it will meet on this director circle. Okay, so and it means that these 2 points here in that case will always be conjugate points. So let's have a wee look as well and see what happens whenever we turn this ellipse into our circle. So if I was to make this, I think we've put it at 1.57. okay, now if I then adjust the angle, I don't want to do that really, do I? Just alpha. Okay, if I adjust alpha to 0, so now we've got a circle. Okay, now if I was to again move this round in order to get the crossover point, so if I shift that round to get that crossover point, so there we go, crossover point. You don't actually see it there, it disappears at that one, but you will probably see it up here, see it up just about there. Okay, so it's minus 3.1 over 3.14. Okay, now you can see that it doesn't quite cross because I actually moved the value of that slightly, so I'll just shift it back. I think it was 6.3 it was sitting at, so that's 6.3. Okay, so you can see that that again is crossing at right angles, but the difference between this here and the previous one that we saw, which was a force of attraction given by an inverse square law, is that the conjugate point here now sits at 90 degrees. Okay, it doesn't sit diametrically opposite 180 degrees. The conjugate point now sits at 90 degrees. So let's turn this back into an ellipse and we'll finish this off. So we'll make this a value here, say 0.7. We'll adjust this round. Okay, so we can see that the conjugate point is now here, so it means that we can adjust this round here. Okay, we don't need to get it exact. Okay, so it sits somewhere here, and it's going to sit and it's going to cross over on the director circle. So this angle here is the angle between the two conjugate points. So say that's point A and that's point O, then that's point B. So if this angle AOB is going to be the angle that's the angle between both of these points here, which are the conjugate points, So if the angle theta is going to be less than that angle, then we're going to have an action which is going to give a weak minimum. But if it's greater than that value, then we're going to have a stationary value, but it's either going to be a minimum or a maximum. So we'll allude to that again at the end of this video. So I hope that's of use to you, and it kind of covers most of what's in the pages 53, 54 of the Charles Fox book, an introduction to the calculus of variation. So if you like this video, then please subscribe, and if you're interested, then you can stay and listen to the rest of the maths, which goes through some of the derivations of the equations which we've gone over here. Okay. So we're looking at the orbit under MUR, and the equation 1 here has been derived in a previous video. If we were to use the substitution, and we substitute that in order to get rid of the c squared, then we're going to be left with an equation which you'll see at the bottom of page 53 of the Calculus of Variations book by Charles Fox. So that equation is a squared divided by sine 2 alpha cos 2 theta plus beta plus 1 plus cos 2 alpha. Now what we've got to do is we've got to use that equation and find out partial r by partial alpha and partial r by partial beta. So that's partial r by partial alpha in front of you, and we're going to do partial r by partial beta next. Then we've got to do is we've got to go and we've got to divide out these two equations. So partial r by partial alpha divided by partial r by partial beta. Now when we work through that division, you get an equation which you'll see on page 54. I'll just write that out in front, you can see that there. So the conjugate points on a circle given by a direct distance law are separated by 90 degrees, which is pi by 2, as opposed to 180 degrees, which is pi for an inverse square law. We also note that the final conclusion is that if the angle that is subtended by AOB is less than the value of theta, then we're going to have a weak minimum, else we're going to have a stationary point, but it'll be neither minimum or maximum.